All right, hey there, guys. It's the Data Daddy, and as always, just want to start by saying thank you guys for taking interest in my channel. I really hope the content I'm producing is useful for you guys. And if it is, I'd really appreciate a like or subscribe. Um, and anyway, let's hop in. So, as you know, or maybe you don't, but I've been doing a series here on optimization in data science. This is part 4. This is the final part that I'll be doing, at least for now. Um, because really, the series today is on atom, or I guess the video today is on atom, or stochastic gradient descent with adaptive momentum estimation. And this is kind of the default, or the benchmark currently in industry that's used. So I feel like this is, if we can understand everything up to here, then that's pretty good. A good place to start for optimization in data science. This is kind of where I'll leave things for now. Um, anyway, as always, I just want to reference or cite my references or give credit to my references. I'm using Dr. Miller, or Dr. John Miller of UGA's textbook. The link is right here. And specifically, it's Appendix A, which is all about data science and optimization, and how those two are used together. That starts on page 619. So please check that out. It really has a lot of good stuff in there, and it will help you probably more deeply understand the concepts I'm going over right now. Okay, without further ado, let's hop in. Atom or stochastic gradient descent with adaptive momentum estimation is the most complicated thing that we've gone over in this series. So I really hope I can do an adequate job of explaining it to you guys. If not, there's a lot of resources. Like I said, it is the default and the industry standard, so there's a lot of resources online that maybe probably can provide a much better idea than I can. But this is a good one. This is one that I use to get a basic idea, and it's just kind of talks about how Atom takes basically it tries to combine things from other algorithms that made improvement on stochastic gradient descent, and it merges them together to make a even better algorithm. So this is really kind of the culmination of RMS prop and the AdaGrad algorithms working together to produce a better algorithm. So if you're familiar with those, and you already know a little bit about what's going on here. Also, too, this is building off of stochastic gradient descent with momentum. So that was the last video. So if you haven't watched that, I would, highly recommend it. And these videos kind of build off each other. So if you haven't watched anything, it might be helpful to go back and watch the others just so that you have an idea of what's going on. So anyway, like I said, this builds off of SGD with momentum, or SGDM, excuse me, and it just adds some tweaks, basically. And some added bonuses here: the fact that this is efficient, and it's really was more or less developed to work with, super large scale problems with lots of data and lots of parameters, so it could require less memory, and really just less computations to get convergence. And that's really what we're trying to do here. Is we're trying to converge, or get to the optimum solution in the least amount of iterations, the least amount of computational power is absolutely necessary. And it's a combination of SGDM and RMS prop, or root mean squared propagation algorithms. I also read that it has AdaGrad in there too, which maybe AdaGrad is part of SGDM. I can't confirm that, but I'm sure that's probably the case. Anyway, so we talked about momentum. We talked about that we want to use the past, basically, to better predict or better handle the future. Is essentially what we're doing with momentum, and that's that was the weighted average before. The only difference now is, so we're taking if you look, we're taking the same thing that we had in the momentum, or in momentum. We're just adding some other stuff in. We're adding this uncentered, or momentum uncentered variance, and then we're adding the corrected mean and the corrected uncentered variance. So basically, these are just ways to get the weighted average of whether it's the gradient or the gradient squared. And this squared term comes from the RMS prop algorithm. But basically, this is just the weighted average of either the gradient and the gradient and the momentum that we talked about before, or the weighted average of the gradient squared, and essentially the I'll call it the squared moment, or the maybe we'll call it the uncentered moment. Basically, it's the same thing as the moment. It's just instead of the gradient, it's of the gradient squared, and it's just that past value. So really, we're looking at the gradient and the gradient squared in this case, and taking both of them into account. Another difference here is the fact that now instead we want, and notice how here it says exponential moving average. Okay, so now we want to exponentially weight these. So basically, all we do is we're going to divide by 1 minus this beta, which is a tunable parameter, raised to the time step. And all that does is that's going to, as time progresses, we're going to weight these parameters, or our hats, are corrected. We'll call them our corrected momentum and uncentered momentum or uncentered variance. We are going to weight these less and less as we go. And the idea here is that in the early stages, the early iterations, where the time step is low, these are going to have full weight, or they're going to be given significant weight. And that's going to allow, in the early stages, us to converge very quickly. It's going to push us down very, very quickly towards convergence. And then as the time steps grow, or as the time steps get bigger and bigger, this weight is going to back off exponentially. So you think about it, the curve is going to go like this. So if you can think about an exponential curve, let's draw one out really quick. So it's going to look something like that. So here's our axis. As we have time progresses in this direction, and then we have our call this p hat and v hat. So as we move through time, these are going to exponentially decay. So at the beginning, we have these really high values, and we're going to make a lot of impact. And then as we move towards time, they're going to make less and less impact as we move further and further out. So that's kind of the basic idea. We just want to push to convergence as fast as possible. Okay. So that's really the broad idea there. And so now let's look at the parameter update term. And we see that we're taking our corrected mean, or our corrected moment mean, I should say, and then we're dividing that by the square root of the uncentered variance, and then we're adding it with this some really basically all the EPS is just some value to keep us from dividing by 0. So it could be whatever you want it to be, but it just needs to be a really small number. I think conventionally, or in Python, it's like 1 e to the negative 8, or like 10 times or 10 e to the negative 8, or something like that, but it's a really small number just to keep it from being a divide by 0 situation. So basically what we're doing here is we're taking this momentum and we're trying to make it so that it is very impactful in the beginning, and as time goes by, we factor it less and less. And that's what we're doing here. So hopefully this was helpful. And if you do need some more guidance in this area, there's tons of stuff out there on it, and I'm sure that between that and this, it can give you maybe even a better idea of what's going on here. But unfortunately, this is such a interesting topic, or such a big topic. I could spend like 30 minutes talking about just this. So for better use of time, we will just leave it at this now, and we'll hop into the code. So, and just one thing I want to do here is I just want to compare this to SGDM. So notice we have, this is the exact same. So this is the exact same. This is the same, but we've changed the way we update the parameters, and we've added a bunch of other things. We've added this exponential weighting, and we've added the way that we're actually updating our parameters. So that's what we've changed. We're going from SGDM to Atom. Okay. So another thing I want to talk about too, or I want to implement here, because this is the way that the optimization algorithms really work in real life is they typically apply some kind of stopping rule. So, and it's funny, I couldn't really find a lot of good examples on the internet, but I know that there is um, like one, it's called the patient stopping rule. So that's what I'm going to use today. But basically, we'll just pick the metric we're trying to optimize, in this case SSE, and then we will basically we'll keep going as long as it's improved, and then once it stops improving, we'll give it a certain number of iterations to improve again. Otherwise, we'll end the algorithm. And after some googling, I found there was a rule of thumb about 10% of the total number of epochs is a good place to start. So we'll start there, but we'll leave it open as a hyperparameter so we can actually tune this and maybe make it better. Or some cases where it's stopping early, we can change it and make it longer, or whatever the case is. Okay, so again, this is perceptron with atom, and then also we're applying a stopping rule. So again, same imports as last time. Just be aware if you have an M1, you may have some problems with the TensorFlow here. But this is just, you could look at the activations up yourself, but I just like it so you can, it's easy to type, activations.sigmoid or .relu or whatever the case is if you want to use different ones. So that's why I've chosen to use this library here. Okay, and so again, same data set we've been using, x, y, three different x parameters, a y target, and we're just going to split those into an input and a y or a target. We're going to initialize our B matrix with some, random or some values, and you could set this to random if you want. I just had this example from somewhere, and these were already here, so we just decided I was going to use those. But up to you how you want to initialize it. Again, we've talked about this in the past video, but this is just a function that grabs our SST, or sum of squares total, based on the target, or based on our y values, and then returns it. This is a function that takes in our data and then how many batches we want, or sorry, the batch size, and returns a list of batches. Now this, as I've already talked about before, this only returns a list of indexes or row indexes where this data lives. So it doesn't actually give you the data, it just gives you a list of where it is. This function actually goes and gets it. It goes and retrieves that data for you based on the batch list. This function calculates our gradient for us, which we've already talked about in previous videos. And here's that activation function. And you could easily change this to tan H or sigmoid or ReLU or whatever you want. So I just think it's nice that you don't have to really worry about the specifics here. Let's see, and then again, hyperparameters. So lots of hyperparameters here. So some of these we already know. So again, we're setting B to new params because we don't want to have to update it every time we want to reinitialize the loop or rerun the loop. Let's see, this is our SST value. We only need to get it one time because it doesn't change. Max iterations here is 100. Our batch size is 5. And again, this is changeable. We only have 10 data instances in this case, so you could change it to 2 or whatever. It also should work for other things like 3, even when there's not a, it's not evenly divisible. Although you may get a weird value with a, batch size of 1 or something weird like that. So I would just keep it at 5 or 2, but feel free to experiment, and you could always import your own data and do something else as well. Eta, again, I found that 0.1 seems to be a pretty good learning rate. I can't remember if it's 0.1 or 0.01 or what it is in Python is the initial value, but 0.1 seems to work well, and that's something we can experiment with later. Here's our beta 1 and beta 2 values, and these correspond to beta 1 and beta 2 here in our formula. I tried to make everything as close to the formula as I possibly could, so that way it kind of makes sense what we're trying to do. Let's see what else. Here is this EPS value I talked about, and again, I said 10 to the 8, but I just said 10 to the negative 10. Again, it just needs to be a small number so you don't divide by 0. And then this is the place where we define our stopping rule. And again, if you don't want to use it, I just made it so that you can set this to false, and then it won't use stopping rule all. So I just try to make it like an on-off switch that you could use if you want or don't. The stopping rule. This is basically saying here we want only to keep trying for 10% of the total number of epochs if there's no improvement. And then this just calculates how many actually epochs that is based on the max iterations we've set, or the max number of epochs we've set. And this is what I call a sensitivity factor, and this is something honestly I made up. Does it seem to make sense? But basically, what we do is we'll talk about it down here. But we take the difference between the updated parameter and the old, our error, and we just make sure that if, and the reason I made it a percentage rather than just making sure that it improved was because there's so much noise that if you only make it that the new parameter has to be, the only condition is the fact that the new parameter has to be better than the old, well then this stopping rule will never work, because there's too much noise in the data that there will always be something that's better than the iteration before at some point. So anyway, that's a long way of saying this is just a tunable parameter that affects how sensitive your model is to changes in error, and you'll see what that looks like in a bit. But okay, so we're getting in. This is actually the meat and potatoes here of Atom with SGD with Atom with a stopping rule. Okay, so we're defining our terms. So we said P is momentum mean, V is the momentum uncentered variance. There's the P. This is the same thing as we listed out above. They're just spelled out as variables rather than as pretty equations. TS is time step. That was T in the past. I think that's really the only difference, to be honest. Okay, so now we need to initialize some things. So we need to initialize a new best and an old best, and this is part for the stopping rule. So we'll actually go over that later, because that's one of the last things we want to talk about. We need an incrementer, so I just set it to 0 here. And again, remember the outer loop handles our epochs. We're going to get a list of index positions for our data, or we're going to get basically all the rows that we want to include in each mini batch, and then a list of those mini batches is going to be returned here. We're going to store all of our momentum values. In this case, it's momentum and uncentered variance, and then the adjusted or the corrected list. So basically, it's just these parameters, and we want to store all of them so that we can go back and get the previous and then the current. Very similar to what we did in SGD and then also SGDM. Another thing we need to do too is we need to set the time step equal to 1. Notice that this is not 0 because the way that it works out, the time step starts at 1, not 0. So if we started at 0, it makes the math funky. Although this, anyway, we'll see what that means in practice later. But we need to set it at 1, not 0, and it's incrementing so that we can exponentially weight or exponentially decay our variables as we go through time. Okay. This is, again, I said this is part of the stopping rule. We'll go over that later. But again, for batch and batch list, very similar to what we've done before. We're going to go grab our batch values. We're going to calculate a gradient. We're going to get our sum of squared errors. Again, stopping rule, we'll talk about that later. Now here's the meat and potatoes. Here is the new stuff that we're actually really adding. And this is, it's very similar to the way that I handled it for SGDM. But basically if, and in the other case it was the increment equals 0. But in this case, it's the time step equals 1. So if time step equals 1, then we're going to do this because we don't have any previous values to use. So we have tweaked this formula a little bit to take out the previous values. So for example, here, right? This only applies if we have a previous value. So we don't have a previous value in this case, so we don't need this and we don't need this the first time we iterate through, right? So that's all we're doing, is we're just taking that off for the first iteration because we don't need it, and then we're adding it back after the first because we will need it. So hopefully that makes sense. All right, so that's our first time through the loop, and then every other time we go through the loop, we're going to be using the full equation, and it's just, you know, simple as taking those formulas from above, sticking them in here, and letting, you know, the algorithm do its thing. So, and then just keep in mind we're appending all of these to a list, and the one thing I wanted to explain here is that this looks funky. Sometimes we're subtracting from 1, sometimes we're subtracting from 2, and the note here should explain it fairly well, but basically, you know, sometimes we subtract from 1 because we had to start the index at 1. So every time that we want the current value, it's -1. Every time we want the previous value, it's -2. And remember, whenever we're looking at just the p and the v, so that the moment and then the moment mean and the uncentered moment, we need to take we need to factor in the previous value. Not only the current gradient and the gradient square, but also the previous gradient, or I guess moment is what we would call it, and the gradient squared. What is that even called? Uncentered moment uncentered variance. Sorry, sometimes I get terms a little jumbled in my mind. Okay, and that's all we're doing. We're making a list of those, and then like in the past, we're updating based on the current value. I know it says -1, but since we started at 1, this is actually the current value in the list we've created. So, and again, we're just updating those weights, and then we increment the time step at the end. And then we save, you know, like last time, we save all the values so we can plot them. Okay, the last thing we need to go over here is how we determine how we want to stop. So let's see, where do I first initialize? And also, we don't need this. We really only need. Let me just make sure. Oh no, I'm sorry. We do need this because we're using it for the stop rule. My apologies. All right, so we initialize this this incrementer for the stopping rule. Okay. Basically, what that's for is, so if you stop, so if this value we initialized right here, if this is true, so indicating we want to use the stopping rule. So if that is true, then we will take the absolute value of the new best minus the old best. So basically, our best SSE, or whatever is the new best SSE minus the old, okay? And then we are going to see, okay, is that bigger than the current best times our sensitivity value we set? And this will make more sense when I actually like print everything out so that you can see it. But in fact, we'll go ahead and I'll print these out so we can see them whenever we run it. Should be another, yeah, go print ink. Okay. There we go. But basically we're just saying it has to be above a certain threshold. If we're only making like tiny progress, then we don't care. We don't care. It's not good enough. We're just going to end it early. Is all that's saying. And then so okay, so if the way this really would read is, if we are making substantial progress, continue to update. Else, if we're not, then increment the counter. And then if our counter gets so big that it equals our stop value, which we defined here as a percent of our maximum iterations. So exactly 10% of our maximum iterations. So if we equal that value ever, then we're going to stop. We're going to break out of this algorithm, out of this loop, and we're going to be done. So that's how that works. And then this part right here, all we're saying is every time we go through and we get a new SSE value, is this SSE, is it better than our old one? And if it is, we assign that to new best. So basically every time we get a new better update value or a new better SSE value, we're going to let that be the new best. And then here we're checking, is that new best relevant enough for us to actually, actually update our parameter based on this sensitivity level that we've drawn here, or we've created here. So that's how it all works. And then of course, as always, we're gonna plot it, and let's see if this actually works. So just to show you, we're gonna make this false first, so we can see what it looks like without it, and then what it looks like with it, and we can see if it's actually working. Okay, TensorFlow. Okay, so there we go. So as you can see, we converge very quickly. There's a lot of oscillations, but we converge and everything's looking good. Okay, just to show right off the bat, let's say, all right, man, like we converge really fast. Like we don't need all this stuff, right? This is too much iterations, too much computation. We don't want that stuff anymore. So what we can do is we can come up here, and we will turn this to true. All right, and then we'll run it all again. And now, oh, there we go. 1% stopping rule factor has been reached. Algorithm's exiting, and it's, we stopped at 30 parameters instead of, or 30 iterations instead of 100, with pretty much more or less the same result. So that just shows the stopping rule is working. It makes sense to use in this case because we don't really need all the iterations. And then back to what I was saying, we can see here the difference between the parameters. So basically, what we're saying here is, okay, is the difference between these parameters, is it significant enough that we want to save the value? And if it's not, we're going to increment our counter. So we're saying, as you can see in this case, both of these updates had a significant drop in error that we wanted to, like this was about 50%. This was about, looks like 30%. So anyway, big percentages. And then in some cases, we'll actually look at the whole thing. And then again, so we updated for last time here, and then there were no more significant updates after that. We reached 10 iterations, and then we stopped. So it did everything that it was supposed to do. So that's good. So other things we can do, and this is, what takes a while is, tuning this thing, because now we have so many parameters, right? We have eta we can tune, we have beta we can tune, beta 2, batch size, we can tune the sensitivity. So all of these things we can do to, make it converge. Let's just, let's change it to a point. Let's change one at a time. Let's change beta 2 to 0.1 just to see what happens. Okay, so it looks like it's, much more jagged in that case. Didn't really change. Didn't help us converge any faster. Really. All right, let's see what happens if we take this one to 0.1 and leave this one at 0.9. Let's see if that makes any difference to us. Okay. Looks like it actually made it go longer in this case by maybe a couple iterations. Maybe helped push us down a little bit faster and smoother, so that's good. Let's see what happens if we tune them both to 1, or tune everything to 0.1. And rerun it again. Oh, wow. Okay, so there we go. That actually, not only is it a little bit smoother, it also, we stopped well short of our 30 plus iterations. So again, just showing, by the way that you tune this, you can actually, push things to convergence much more quickly or slowly. And it really, it is a process of tuning your model based on these inputs. So a lot of things to consider, and there are packages and things that will actually go through, and like there's auto keras in Python, which if you use that, will actually do a lot of this parameter tuning for you and just give you the optimal model for your data set. So you don't always have to do this tuning manually, but in this case I'm just going through and showing you what it would look like, or what it could look like. Anyway, but I think you guys get the idea at this point. Again, sorry the video is so long, but I think this was a fairly complicated topic, and I hope that all those things made sense to you. As always, if something didn't make sense, please drop me a comment, or you'd like something explained more, drop a comment, and I'll see if I can make a video on it. Anyway, guys, as always, if you enjoyed it, please consider giving me a like or a subscribe, or both, so I can continue to grow and get better and produce better content for you guys. Anyway, guys, yeah, so do that, comment, and again, thanks so much for watching, and hope you have a great rest of your day. Bye-bye.